Lindsey Richland, thanks so much for coming in and talking, and also maybe more importantly, coming back to UCI after being at the University of Chicago for so many years. What motivated you to come back to UCI?
Yeah, well, thank you for having me and for bringing me back. I mean, I'm really so pleased to be back here. I really love, and I think that the university, UCI's School of Education is very unusual in that it has a very collaborative, collegial atmosphere. There are so many people doing work in classrooms, but that's also very sort of mechanistic, very kind of deeply theorized, that it's something I really missed being away. And actually another piece that I really love about the school is that there's a close integration between the teacher learning piece, the teacher credential program, and the, very, sort of theorized academic research that isn't always the case in all schools of education. So I love that since being back, I've already been able to teach in the MAT program as well as, the PhD program and working with the undergraduates. So it's altogether a really rich, vibrant place. And also, really diverse and serving a really just important population of undergraduate and graduate students. So altogether, really, it's a great place to be.
We're so excited to have you back here. Let's talk a little bit about your research on math education and kind of what makes it distinct. Starting out maybe about how you think about math as an area of study.
Yeah, so I take a view of mathematics education and of mathematics more broadly as being a really exciting place to do thinking, reasoning, creative problem solving. And that's not always the way that people view mathematics education, right? So, there are people all the time, standing up and saying how much they hate math, how they're not a math person, math makes them anxious. And it's sort of that's part of our fabric on how we talk about math, but actually it's really, but yet they love puzzles, they love problem solving, they love, figuring out, their way out of some sort of a complicated situation, right?
Escape room.
An escape room. I mean, anything like that, right? And so, really that's what math is. That's why mathematicians love it, If you ask, mathematics faculty who are teaching these classes, often they say, I love math because you don't have to memorize anything. You can think your way through problems. So I really want students to get that and to sort of rethink the way that we teach math to get students excited, build on their initial knowledge about numbers. We know that babies are born attentive to number. This is true in a fair number of animal species. These are true with our babies. We're already predisposed to attend to things like quantity. And so, let's build on that. We're born creative. We can pull those together and get more kids excited about math.
And your particular expertise is on cognitive processes and things like executive function. How does that relate to math?
Sure. So executive function is it's a limited capacity system that we have, everyone has in their minds, that basically governs how we shift our attention, sort of draw our attention to specific aspects of our environment, how we disattend to things that are not relevant, and how we decide what to attend to, and then we take some of that information and we manipulate it in mind. So for example, if you're doing a mathematics problem, trying to add 473 plus 231, you have to hold a lot of that information in mind. You have to disattend to everything else I said. You have to hold those numbers in mind and manipulate them. That's within your working memory, right? So that's pretty taxing. So in a mathematics classroom, there are lots of demands that are trying to take children's executive function, right? So there are peers and there are instructions for the task that the teacher might have given. There are also the demands of the task itself. And so if we want our kids to be thinking creatively and in rich ways about mathematics, we want them to have available executive function resources to think about, why does this matter? Why would that be true? How do we, wait, is that like the problem we solved before? Ooh, maybe I can take an idea from this one and try to use it to solve this. So we want them to have enough available resources to be able to think generatively and creatively about mathematics. So we want to be careful to not overwhelm them with other aspects of these problems and the tasks. And so I do a lot of work trying to think about how to balance those demands. Like, for example, putting a lot of information on the board so kids don't have to hold that in mind. So if I asked you to do that arithmetic problem, I gave you in mind, that takes a lot of resources, but if it's written down, it's much less, right? Teaching them techniques like, writing out the steps of an arithmetic problem allows them to offload those working memory resources, and then they can kind of spend their time actually thinking in more interesting ways about the math that they're doing. So I do work, trying to figure out strategies for reducing those loads, and then I do, other work working with teachers, trying to, think about what are really feasible, practice-relevant ways to incorporate these into just an everyday classroom.
Right. So this has implications directly for kind of how one teaches. This is related to kind of students' feeling of anxiety and stress, pressure.
That's right. Yes. So another thing that goes into math classrooms is that, and another thing that our executive function gets used for is to kind of hold worries in mind. So if we're saying to ourselves, oh no, it's math, oh God, okay, this is a big problem, I have to do well, or, any other kind of verbal kind of self-talk, that is also taking your working memory resources, right? And taking these, it's shifting your attention. So what we find is that, and a lot of research has shown, is that, children who are under pressure, who are feeling worries, tend to have reduced working memory capacity to spend on other things and on the tasks that they're working on. So they tend to use less high executive function requiring strategies. So things like they're trying to just memorize, just sort of pop out whatever is the simplest solution. And that works if it's a low resource kind of a problem, but it doesn't work for doing more rich, generative, conceptual mathematical thinking. So also my work is trying to understand that process, understand these relationships between pressure and mathematical thinking, and to develop strategies and teaching tools for not only reducing pressure, so we do both things, reduce feelings of worries, but also teaching in ways that lower the working memory demands of the instruction itself to the point that even if you have worries, you can still engage with this content. So trying to work on both sides.
And you have two active IES, Institute of Educational Science grants right now. And of course, IES is all about interventions, how we can make a difference in terms of student learning.
Yes.
Tell me a little bit about the interventions you're working with around these issues.
Sure, yeah. So the way, both of these are grants that are still at the point of trying to understand the intervention process. So we don't have a big packaged intervention for, large scale sort of implementation. But what we're doing is we're running experiments to understand whether we can reduce the load in a classroom context and thus produce, more conceptual learning for students. So the first study is looking at ways of offloading working memory by using visual representations. So using things, like I said, leaving things on the board, or giving students worked examples, so other previous examples that are kind of have all the solutions worked out, that then allows them to really remember what was done before, and then they can sort of draw in more conceptual ways on that when they're solving new sorts of problems. So rather than having a child have to remember everything that was said, this provides them these visual representations. Another technique that's been recommended for use in classrooms is to have teachers lead discussions where students describe the different ways that they've solved the problem. And that's really nice because it teaches students that math can be solved in lots of different ways. There's no one way to solve a problem. So they see lots of students doing different things. However, that imposes a lot of demand if you're actually going to remember 3 different solution strategies and try to figure out, are they the same thing? Are they different? Are they both okay? Was one of them a misconception? So again, in this study, we manipulate whether the students get to see those solutions written down, left there for the whole lesson, so that if they're all written down, they have lots of time to look through and compare them and understand these differences, versus what is a more typical U.S. teaching practice, which is just having the students verbally say what they did for these strategies. So so that's really, these visual representations are sort of the core piece of these interventions.
And is this research classroom-based, where you're going out into public schools to work in classrooms, or are we bringing students into the lab to kind of experimentally manipulate the treatment?
Right. So I think we've hit on a really neat methodology. These are in-classroom experiments, but we're really trying to walk the line between ecological validity, so real relevance to real everyday classroom settings, but also maintaining experimental control. So what we do in this methodology is we actually, before we even start the study, we work with a classroom teacher and we collaboratively develop a lesson. And it's a lesson that requires higher order thinking, lots of this generative creative thinking, comparing multiple solution strategies. So we kind of develop the lesson. Most of our work is on proportional reasoning, or teaching how to handle proportions in school, which is a conceptually demanding topic, mathematics topic. It's part of the curriculum, part of the state standards. So we create this lesson, then we have the lesson taught in a real classroom with real kids, and we videotape it with at least 3 cameras, with microphones everywhere. And then we use video editing to create a sort of a lesson that then we can manipulate. So we can have one version of this with visual representations and another version where the student just hears other solution strategies orally, for example. And so these are the exact same lessons. All the crazy things that happen in a real classroom happen here. Kids say things that don't make sense, or someone is being distracting and making a joke, and all of those things happen the same in these 2 conditions. But one, you get the visual representations, and one you don't, or whatever the manipulation is. In this case, that was it. And so we have these 2 versions. Then we take those into our actual experimental classrooms, and we turn them into interactive lessons. So there are pauses while the students, answer things. And within classrooms, we assign kids to each of these 2 conditions. So that way, we have controlled video lessons, but we can also randomize assignment all the way down to the within classroom setting. So it's, and the kids are then interacting with the video lessons. It's not the same as their real teacher, but they're working with this video lesson. They're in their classroom with their peers. So again, they're still being distracted by peers talking and, kind of having these same sorts of executive function demands that you would have in a real classroom, because they're in a real classroom.
And where is this research heading to? Well, what's the direction you're hoping to kind of move in
around
this work?
Yeah, so the plan is, so now we have these 2 versions, right? And we've run one study. Next week we're starting the second study, and these are really big studies, lots of data collected, so we know a lot about the kids that are participating in these lessons. So we know, who is this working for? Who does it not make a difference? We know a lot about their cognitive profiles, their executive function, their prior knowledge, all of the things that we think are going to play into their learning. So the hope is that we'll better understand, when these teaching practices are useful, when they're really effective, and the next step will be to intervene with teachers, and so to build interventions that are a more direct intervention, and then we can look at the effects of teachers actually, invoking and using these practices.
What drew you to math education in particular, and these cognitive processes in your own life?
Yeah, I guess there are a couple things. I was always, from young childhood, always really interested. I remember having this feeling of, just thinking it was amazing how minds work, that like kids learn, and like, I don't know, babysitting and things, just like watching kids learn things was so fun, and watching them change over time. I mean, so I've always been really fascinated with that, I think, as a topic broadly. I worked in a school in the summers, and, sort of trying to, I don't know, I always kind of was engaged. And then in college, I was actually an anthropology major, but there I actually did my, a lot of my research work looking at, sort of cultural differences within classrooms, and how sort of teacher practices, interacted with cultural differences that children were coming into the classroom with. And so I kind of continued my focus and interest
Which
in
still is kind
education
of related to kind of the stress and pressure and anxiety, right?
Absolutely.
That you're focused on.
That's right. Yep, absolutely. And I'm really interested too in sort of home contexts and relationships to classrooms, and sort of, home socialization of like, what do you attend to? Do you, memorize what's being told to you? Do you question what's being told to you? These kinds of just home routines interact differently with, sort of teaching practices, right? I will say, growing up, I had this fantastic teacher, Dr. Wong, who was my math teacher for calculus in high school, and he used to give us these problem sets that were these kind of crazy problems, and we'd all go home, and like be on the phone, me and my group of friends, like trying to figure this stuff out, and asking each other questions, and it would be pages of like proofs, and and it was just a lot of fun, right? And it was a totally different way of engaging. He was Chinese, did I say that right? And so he was sort of building on, I think, a really different model of how to teach mathematics, and so that was in my head. And when I went to graduate school, one of my dissertation advisors was Jim Stigler at UCLA, who at that time was directing the Third International Mathematics and Science Study, which was a videotaped survey of math teaching around the world. And so I got really excited about looking at teaching practices around the world, and sort of drawing ideas on just really different ways of conceptualize math. Because you sort of think math is math, right? I mean, this is the same the world around, but actually the instructional practices are really different, but they tend to be very common. They're sort of within a country, the variability within a country is much less than the variability across countries. So you find that, the routines that we use here in the US, if you have better and worse teachers, you have really different practices, but really our routines are all pretty similar. So I was interested in trying to draw new ideas and sort of think about how to do that. So now I'm really interested in, I also got interested in graduate school in the cognitive piece, and sort of trying to think through how do you draw on children's developing abilities, how their minds work, and have some really fresh ideas about how to engage their thinking in a classroom setting.
This formative experience you had with this calculus teacher in high school.
Yeah. No, I mean, that really opened my eyes to the fact that there were really different ways that you could engage with mathematics, and and it can be really fun, and it can engage your problem solving and excitement. So I'm really interested in trying to build that into the way that both teachers and students think about math in the U.S. And there are these very strong cultural differences across countries regarding kind of normative ways of thinking about teaching mathematics. And so, while you don't want to pick up a strategy used somewhere else and just imagine it's going to work perfectly, in a U.S. classroom, you can get some ideas and sort of, shift our thinking a little bit, sort of become aware of what our cultural, expectations are about instruction, and then, so I'm trying to draw some of these new ideas and try them out in classrooms in ways that work in the U.S.
Yeah, well, it seems to me that some of the debates around math instruction are really kind of about the culture wars that are occurring in our country right now. And is there a way that your approach around educational science-driven approach can cut through some of that cultural discord?
Right. I mean, I hope so. I mean, that's really my goal, is to very deeply understand classrooms and the way that they function, and the really amazing job that our teachers are doing, guiding, 30 minds in, from what they know to something new. I mean, it's a really amazing job, right? And, and you have to be aware of so much. And I mean, so I'm trying to really be very thoughtful about that. And then, draw on what we know about sort of, provide value added information, right? Bring in what we know about how children's minds work, things like executive function, and bring in new ideas from other places to try to, kind of build experiments that are situated in classrooms and thus provide insights that are much closer to what teachers are already doing.
So there's also another study, IES study, on socialization in the home, in the classroom. Can you describe that study a little bit for us?
Sure, yeah. So I am part of what I think is a really amazing longitudinal study that has followed 60 typically developing children and their families, and 40 children with early traumatic brain injury. From 18 months of age until now, they are on the cusp of graduating high school, so going to either college or into careers or disengaging after high school. So we're really interested in understanding how sort of home practices, sort of home socialization contexts relate to these educational trajectories. And I think what's really neat about this project is that the early part of the study, which happened before I was part of it, this is work collaborative with Susan Golden-Meadow and Susan Levine and Steve Raudenbush at the University of Chicago. The team videotaped home context, just everyday language, for 90 minutes, 3 times a year. For the first 5 years of these children's lives, and all of that language has been transcribed and sort of carefully analyzed. And I've been part of analyzing that for how parents are using higher order thinking talk, what we're calling higher order thinking talk. So sort of asking questions like why, because, asking children questions, children asking parents questions, really trying to understand what the sort of discourses around, thinking and reasoning look like in the home. And we look at also, talk about the natural world, sort of proto-science, and we also quoted when they do talk about, early mathematics. And then we follow these kids so that every year from, 5 years on, the children's cognitive, language, and school skills were analyzed or were measured. So as I say, now they're in high school and we know a lot about kind of what their educational trajectories have been. We also have videotapes of parents and children solving problems together, so we can try to understand how these parents are sort of socializing children's thinking and reasoning skills. And we know about their school performance, so we can try to understand how these align easily with school settings, how they don't align with school settings as much, so whether children are going to be kind of socialized in different ways, right? And then as part of that project, we now have IS funding to do some intervention work where we take some of these kind of normative routines from home and try to capitalize on them to have teachers intervene with sort of language practices that are kind of building children's, again, thinking and reasoning in mathematics contexts. And so trying to, kind of engage with some of these home practices to shift attention within classrooms to asking questions, trying to figure out the whys, and sort of harness that in a context where maybe they're not expecting to be thinking about the content in these ways.
And unpack a little bit for me the comparative piece. So there's a sample also that has these traumatic brain injuries.
Sure. So the other piece of the project, and this piece is directed by Susan Levine, is really been looking at, again, these are kids for whom brain plasticity means, they can have, really outcomes that don't look different than kids in our typically developing sample, or some of them have outcomes that look a lot different. And so we're that allows us to understand more about how the brain, sort of function and particular resources interact with these language practices to yield different educational outcomes. So it allows us a little more information about sort of how the sort of underpinnings of the neurological underpinnings of the cognitive practices in school settings might actually be explaining performance outcomes.
Well, thanks for coming in today. It was really, really great to have a few minutes to share with you your interest and background.
Well, it's my pleasure. Thank you for having me.